Okay. Hello, everybody. Welcome to first Rust Wrocław meetup after the summer break. The summer was quite long this year, but we are back. We do meetups more or less monthly, if it is not a summer break. And we try to do this at different companies. So if your company would like to host us, we will be very glad to talk. Today we are at Anixe office. They are hosting us for the second time this year. We are very grateful for this. Yeah. Whoa. Yeah, maybe I will leave the splash screen. Okay, anyway, welcome everybody. First talk will be presented by Jakub Trond. He will talk about Merkle trees. I am very eager to learn everything about it. So enjoy the talk and give a huge shout outs to Jakub.
Okay, hello everyone. I honestly expected this introduction to take the organizers a little bit longer, so I'm not fully mentally prepared, but nonetheless. Hello, as aforementioned, my name is Jakub Trond. It's nice to be here, especially given the fact that I actually used to work here 3 years ago. And it's been nice. Except for the entire pandemic stuff that happened around the time. Today I want to give you a talk about Merkle trees. The title of the presentation is How are Merkle trees? Because I wanted to do a little bit of a joke, like, oh, you know, everybody always asks, what is a Merkle tree? Like, how do I use it? But nobody ever asks, how is a Merkle tree? But by the time I actually started writing this presentation and realized that this joke is not that funny, I couldn't be really bothered to contact the organizers and change the title. So here we are. But the reality of this presentation is that it's what are Merkle trees, obviously, and how do we implement them in Rust. In this presentation has like 2 sections. The first will be a small visual theoretical introduction to like how a Merkle tree works, how do we construct it, how do we make use of 2 interesting properties of it. And the second part of this presentation is a semi-live coding implementation session. What's in it for you? Well, at the end of this, I mean, I could say it now actually. I was technically given permission by my supervisor to say that, hey, we're hiring at my blockchain company. So if you're not blockchain averse, you might be interested in learning that a lot of companies will use like a Merkle tree assignment as their recruitment task. This has happened to me twice, for example. So if you learn about Merkle trees, you're quite a bit ahead of the curve against the competition. So without further ado, let's jump into like what is a Merkle tree. It's a tree, as the name implies. We start with a set of leaves at the very bottom, right? Because that's how software engineers imagine trees growing downwards. The bottom set of leaves, right? It could be anything. It could be files, could be abstract user data, could be directories. It could be anything you really want. But for the purpose of a Merkle tree, what ends up in the leaf is actually just a hash of whatever you're actually using, right? So it could be a hash of a file, a hash of a directory, a hash of a website in the index you have somewhere or something like this. Then we take these leaves in pairs and we hash them going up So we hash the first pair, second pair, third, and so forth until we arrive at a number of hashes, same as the number of leaves divided by 2. We do this multiple times until we finally arrived at the root of a Merkle tree, which is a singular hash that represents, as hash properties give you a certain uniqueness and consistency of the data you have. Applications of Merkle trees range from, let's face it, probably if you are learning about the Merkle tree, if you're using a Merkle tree, chances are high you're either working in blockchain or you're interested in working in blockchain. However, during a brief research for this presentation, I also learned that apparently AWS's DynamoDB uses Merkle trees for consistency checking, and this is probably very contentious, but I found an article which explains that Git version control system uses Merkle trees internally to produce efficient deltas of the data that you wanna check that you have the right ones. Even though I'm pretty sure they don't actually call it a Merkle tree in the implementation. But I just think Merkle trees are cool. And you might be wondering right now, how is this different from just concatenating all the data I have and hashing it together, right? For the purpose of consistency checking or verifying that, I have all the right data. As it said, say you don't know that 500 files, you could just hash them together, right? Well, Merkle trees give us two important properties, and the first one are inclusion proofs. Inclusion proofs allow us to verify efficiently that a certain leaf is indeed, or actually maybe let's rephrase it a little differently, contributes to the root hash of the tree. So, for example, if we have here the leaf number 4, do you guys see it, by the way? Is it visible enough? Leaf number 4, and we want to verify efficiently to somebody else, to ourselves, however, that it is indeed part of the set. Well, let's build it from the bottom up. So first, we calculate the hash H2, of which L4 is a part. For that, we need to provide the sibling L3. Then to hash H5, we don't need L1 and L2, we only need to provide H1. And then finally, to calculate H7, we only need to provide H6. So we skip, L5, L6, all the way to the end of the tree. All the data highlighted here is what we would call a Merkle proof. And you'll notice, and this will be important in the later part of the presentation, is that this Merkle proof, apart from just containing the data itself, so like these nodes all the way up the tree or through like a path to the root, it also has a certain sense of directionality, right? Like we need to not only say that our sibling was L3, we need to say our sibling on the left side, on the left with respect to our parent, right? On the left of the branch was our sibling. And H1 was also on the left, but H6 was on the right. Another property of Merkle trees is that they allow us to efficiently update the entire set, right? If we were to, say, have 500 files with 1 terabyte data total, and you want to hash it all together, one file changes, you have to hash it all again. That's expensive. With a Merkle tree instead, even though we do have to store double the data in terms of hashes, right, which will become apparent later, when we actually update the hash, the only thing that changes is the path all the way to the root of the tree. So for example, we updated L4 to Q4, we only update the hash above it, and the root of the tree. But here's me talking about efficiency. How efficient is it really? Before I give you like the big O notation, I want to talk about measuring the tree. So how do we describe a tree? A tree is typically defined by its depth, and perhaps at this point it would be, I should have probably prefaced this before I started the presentation, but I'm not a cryptographer, right? I'm just a lowly Rust software engineer. I just think Merkle trees are cool. So take anything I say with a grain of salt. I might be wrong here and there on like naming conventions or such. But what we're talking about here is technically a sparse binary Merkle tree. Binary meaning it splits into twos, and sparse meaning we have empty nodes which will be allocated to 0. You'll see that later. A depth of the tree is not necessarily, isn't typically how many rows of nodes we have. It is instead how many gaps between the rows we have. So the Merkle tree in the picture is of depth 3, right? And a tree of depth 0 is useless. It's just a single hash. It has 1 leaf and 1 node. A tree of depth 1 has 2 leaves and 1 root hash and 3 nodes in total. A tree of depth 2 has 4 leaves, 7 nodes. You might be seeing where it goes. A generic tree has 2 to the power of depth leaves and 2 to the power of depth plus 1 minus 1 nodes. I skipped the slide. Okay. So how efficient is an update? Well, we only need to update, in reality, depth plus 1 node, right? So if we do an update on Q4, we only need to update, this is a tree of depth 3, right? We only update Q4, H2, H5, and H7, giving us a total 3 plus 1, depth plus 1 nodes. Now you can, I don't have a proof that this is generic in every case for every depth, but I think it stands to reason, right? Let's take a tree of depth 20. I actually didn't double check these numbers, so they may be a bit off, but with a tree of depth 20, we have a little under 1 million leaves and 2 million nodes. Actually, this is definitely wrong. This should have been 1 million. We have a little over 1 million leaves and a little over 2 million nodes, right? But when we do an update of a single item, we only need to update 21. That's logarithmic efficiency on an update. How efficient is an inclusion proof? Same deal. We have a tree of depth 3, and now, depending on how you want to structure your verification check, maybe you have this H7 hash provided somewhere externally, maybe you store it, maybe you provide L4 externally, but in general, it's also going to be logarithmic in terms of memory efficiency for inclusion proofs. Okay, so far so good? Are you guys with me? Are you with me? For implementation, we're Rust developers here, and Rust developers love thinking about memory. So let's talk about memory layout. We have a tree. Let's color the nodes in a totally arbitrary scheme. An initial solution might be to store the tree in a breadth-first manner. So we have the root of the tree in the 0th position in our buffer, the first and second children in the 2nd and 3rd position in the buffer, and so on and so forth, giving us this indexing scheme. However, I know something that you don't, which is that it will pay off greatly if we skip the first node in this buffer and use one-based indexing scheme. For reasons that will become apparent during the next slide, which is index calculus. Now that we have our tree stored in memory in a linear buffer, it would be useful to be able to still operate on it as if it was a tree, right? So we want to ask questions like, what is the parent of node at index 6? What is the leftmost child of the node at index 5? What is the sibling of node 2? And so on and so forth. So what is the index of a parent? Any thoughts, any ideas? Yeah, exactly. It's floor of index divided by 2. Index of sibling, I want you to pay attention to evenness and oddness of the numbers here. Do you see a pattern? If the given index is even, then my sibling is my index plus 1. Otherwise, it's minus 1, right? You can see it clearly here. 4 is even, my sibling is 4 plus 1, 5. 5 is odd, my sibling is 5 minus 1, 4. By the way, if we didn't apply this trick of skipping the first root, for example, the index of a parent is now I plus 1 over 2 minus 1, right? And for index of sibling, this gets just flipped, but then we have the next one, which is depth at index. We also want to know which level a given index is on, right? Here on the top, you have the index of the node in the tree, and below it is the depth. And I want you to pay attention to the leftmost side of the tree, so the leftmost branch. Do you see a relation between the index of the tree and its depth? It's a logarithm, a floor of a logarithm of base of 2, right? Because given that the next level starts with the next power of 2, it stands to reason that all the indices in this level, when logarithmed, will give you a power of 2 plus some decimal points. We also need to think of the children. So what is a child at a given index? What is a child at index 3? And what is the left child at index 3? And what is the child, right child at index 5, for example? We know previously that to get a parent, we divide it by 2. So it should be pretty obvious. I mean, I did this presentation before, so I know it, right? That it's going to be times 2 or times 2 plus 1. Awesome. With that out of the way, let's get down to the implementation. And as I said, this is going to be a semi-live coding. I have a little scaffolding project set up, and I implemented all of the index calculus equations that we just talked about. So we have index of parent, index of sibling, depth of things, etc., etc., etc. Because it's frankly quite easy to implement. And we're going to implement our Merkle tree. Can you, by the way, is the font okay? Should it be larger, smaller, color too bright? All right. For our hashing functions, we're going to use SHA-3, the 32-bit variant. And I prepared a set of tests for us, right? First, we're going to want to be able to implement a tree with an arbitrary initial leaf value and make sure that for a given depth, it initializes with an expected root value at the top. I have these values from like a battle tested library we use at work. So I have high confidence that these are correct. Next up, we want to be able to update a leaf and have this change propagate all the way to the root. This is trivially testable on a small tree, right? We have an initial value for all the leaves set to all zeros. We initialize tree of depth 2. So you will recall that a tree of depth 2 has 3 levels of nodes. We'll update the first leaf to a new value of all ones. Therefore, like you can walk through it without actually implementing the tree, that we expect the root hash to be equal to a hash of the new value and 0 and a hash of a 0 and 0. After we're done with updating, we'll need to update proof generation. Before actually going to proof verification, we'll go first to proof creation. So the first test will give us a proof for the first leaf in the tree, and this is the graphical representation of that. For the first leaf of the tree, what we expect to be in the proof is that the sibling on the first level is on the right side, and its value will be 0, right? Because that's the initial value we'll be using. And the sibling on the second level will also be on the right side, and its value will be hash of two leaves all set to 0.
Could you expand a bit more on what a proof here is? Like what it...
Yeah, a proof allows us to verify that a given leaf contributes to the root in an efficient manner using only O log n items, right? Like say you want to send it across a network or store it in a database or something.
What the people proof is that it's not only efficient, but the non-title proof system do not need to know anything about other members.
Well, they do.
Only about one of them, and you can
Yeah.
figure out that.
Yeah. I mean, in order to create a proof for yourself, you need probably the entire tree.
Great.
Yes. But on the verification side, you only need the proof, right? And the root and the proven value and the logarithmic size of the proof. Does this answer your question? Okay. It's better. So that was the proof of the first leaf. Then we have the proof of the last leaf. So again, the situation will be flipped. We'll have the sibling on the left side set to 0. And then on the second level, sibling on the left side again, set to a hash of 2 0 values. An arbitrary proof set somewhere in the middle. We have a tree here again of depth 2. We create some arbitrary leaf values. We update them accordingly in the tree. So we have a tree which contains 0, 1, 2, and 3. And then we get a proof in the middle. So we should see that on the first level, our sibling is on the right side. And on the second level, our sibling is on the left side. And all the hashes are what we expect it to be. And final test, after the implementation is done and correct, is the verification of the proof. A typical API for inclusion proof verification of Merkle trees is such that it's not a function that throws an error or gives you a Boolean. It's instead a function that accepts the proof, which are all the sibling and their, sides, directionality, if you would. It also accepts the value you're trying to prove the inclusion of, and it returns to you the root of the tree that this proof verifies to. So then you can grab it, compare it against the root you actually have stored somewhere, and be sure that it's correct. Okay, any questions?
Why do we use trees and not instead a hash set? It gives us still, it gives us even better kind of lookup and vision, but it doesn't give us this ordering of the nodes that you mentioned. For example, we would add our L4 from your initial example, and we could check if it's present on the set.
But you have to yeah. But that's the thing is that you have to have a set, right?
Right.
Where with a tree, for example, this is like a blockchain thing, right? Typically, when you say, okay, not a terrible fan of NFTs, but a thing about NFTs is sometimes what they did, right? They wanted to have a initial whitelist of addresses that are allowed to mint ahead of everybody else, right? You could store an array of or a hash set of all the addresses in your smart contract, but storing data in a smart contract is very expensive. So instead, you store only the root of this Merkle tree. You host the Merkle tree somewhere off-chain, and then when somebody wants to verify that they can mint, they just give you the proof, and you're proving that their address is indeed contained with the proof against the root of the tree.
Okay.
Yeah.
Take into consideration the fact that we don't have it's in a distributed context.
Yeah.
Right? So
Well, it could be, but yeah. All right. Let's move on to the implementation then. First up, we're going to want to initialize our tree with a given initial leaf value, calculate all the all the hashes all the way to the top, and make sure it's correct. Firstly, as I mentioned before, in our indexing scheme, the root of the tree is actually index 1. So let's just return that here. And let's move on with implementing our tree. We'll obviously need a vector of nodes, which have initial leaf value. And we have a function already prepared, which gives us the number of nodes. for a given depth. Now this function, you might remember previously in the presentation, I gave you this equation with the -1 here, but you'll know that since we're skipping the index, it's actually to the depth plus 1. It all comes together. It's truly beautiful. So that's how many nodes we'll have in this vector. How do we initialize all the hashes inside it? The rightmost, the rightmost, I don't think that was correct, by the way, but the rightmost part of the hashes is already initialized, right? So we need to only initialize the, the second level, third level, and the root of the tree. Let's start off with a recursive implementation. In this recursive implementation, we will start at the top and recursively hash the children at the bottom level all the way until we get to the actual bottom of the tree. And then, through the magic of recursion, we end up back on top. How do we, what will be our exit condition from this recursive function? The answer is actually quite simple, which is that if our left child is outside of this buffer, right? So we get the left child at this given index, and we can compare it against the number of nodes we have allocated, right? So if it's outside of that, we know we've reached the end of the tree. And sorry?
Yeah, I was wondering.
Yeah. Otherwise, we'll get also the right child. Thank you, Copilot. And hash recursively. Oh, sorry, I forgot to mention, I suppose, that there is a concatenation function here already prepared, which grabs the two hashes together, concatenates them together, and gives us the resulting hash of that. So we hash recursively the left child, we hash recursively the right child, and we set nodes at our index to be a concatenation of the nodes of left child and nodes of right child. All right. And we have to recursively hash starting from the root of the tree. In the tests, and fun fact, if you're not familiar with the syntax, this comes from the test case crate, which has been developed in this very company by a member, by an employee who no longer also works here, but I highly recommend it. You'll notice that we have a depth of 5, 7, and 20. You might recall that for depth of 20, we have a little over 2 million nodes. So we have to hash half of that. So that's 1 million hashes, right? And you'll notice that it's a bit slow. Does it have to be?
When you construct the string, right?
Yes.
From the start.
From the start, from initial value. It doesn't have to be like that. There must be a better way. Sorry? I have here, yeah, so we have a little over 1 million hashes to do, but we don't have to live like this, okay? You'll notice that all the initial leaves are set to the same value, right? So all the hashes on the second level are the same. All the hashes on the third level are the same, right? In reality, we only need to do how many hashes? Depth hashes. Depth number of hashes, or give or take plus minus 1, right? So let's do that instead. We'll abandon the recursive approach, although I suppose you could do like a memoization here to do that instead, but I prefer this, which is we'll calculate the initial value at given depth. Initially value, and and this has to be depth plus 1 because you'll recall depth actually refers to the number of gaps between the rows, so we'll need plus 1, right? Then to calculate these initial hashes, we want to go from like starting at the second to last value and hash it using the last value, and then step backwards, right? So we're going to go for I in 0 to depth reverse. And we're going to say initial value at depth I is equal to, oh yeah, thank you, Copilot, exactly that. Now, instead of hashing recursively, we can simply go through all the nodes in the tree. Get the depth. And set the appropriate value using initial value at depth. And if I didn't make any mistake here, it should be vastly faster. All right. 15 minutes to go. I think our time is good. Next up, we have the set function. The set function should update a leaf in the bottommost row, right? And then propagate this update all the way to the top of the tree, resulting in the root change, right? I'm also going to do a recursive implementation here, but you'll notice here one thing is that this function accepts a leaf index, right? It's not an index into like this node structure, so we have to convert it first. And we're going to use again the fact that I think I'm mentioning ad nausea right now, is that the number of nodes is 2 times the number of leaves. Therefore, we just need to offset by the half of the length of all the nodes that we have. So our index is just not 3, like that. In order to update the tree itself, we're again going to go with a recursive approach. This time we're going to go bottom to top. So we're going to update let's just start writing this because I think it ends up being a bit funny. In a morbid way, which is that we'll go all the way to the top until we don't have a parent, right? It's going to be if, actually, let's use the hot off the press. And if we have a parent, we're going to get our sibling. We also need to know whether or not we are the right sibling. So simply check that we are, sorry, this is wrong, is left. That our index modulo 2 is indeed 0. And if we are on the left-hand side, we update node of the parent to be equal to that of a concatenation of the newly updated value. And what? Oh, it's an option. And the sibling on the right-hand side, otherwise the sibling will be on the left-hand side. And we do so all the way until we end up being a node without a parent. Set recursively nodes parent. So first we'll update the actual value that we want to update, call set recursively. And if I didn't make a mistake, then I think this should work. It does indeed. The function is, the test is not aptly named setRoot, but should be probably update the tree, but it works nonetheless. Is everything clear so far?
On what basis do you choose the index of the leaf to place for element?
What do you mean?
How do you know if the leaf is free to be used?
Well, I update an arbitrary index, right? It is up to the user of the Merkle tree to choose how they want to store it, right? For example, maybe you store in the Merkle tree the addresses of some wallets that you want to be included in a whitelist of some sorts, right? So then you will also need to store some index for yourself that will let you know, hey, the next free index is this, right? Or maybe you just go by which values are set to 0 at that time. By the way, something that I didn't mention, I mentioned that this is a technically sparse binary Merkle tree. It's sparse because it also provides an additional feature of proving non-inclusion, right? Not only can we prove that a certain value is present in the tree, we can also verify that it is not present in the tree because all the initial leaves are set to 0.
But for proving, you also need to provide an index, right? Which you want to prove.
Funny thing, kinda yes, kinda not. So you don't need to provide an index. You just need to provide the leaf value and all its siblings all the way to the top, right? But I started making a graphic for that, but I had abandoned it because I thought it would be too esoteric knowledge. There is a certain interpretation of an binary representation of an index of a tree that it is also its path in the tree. Let me try and explain it without a visual aid. If you take 4, so 1, 0, 0, the 0 means we go to the right, 0 again we go to the right, right? And the same will be true for 7, right? 7 will be 1, 1, 1, so we go left, left. 5 will be, hold on, I have, 1, 1, 0, 1. 1, 0, 1, so we go left and right.
It's basically a binary color.
Yeah, and so that's kind of what I'm getting at your question, is that you don't need to provide an index, but by virtue of providing the directions in the path, that can be decoded into an index.
Okay, but well, it doesn't solve anything because you must know the location of the leaf which you want to check.
If you want to get
location, either it's an index,
yes,
or this.
If you want to get the proof, yes, but if you already have the proof, you don't need it.
Okay.
Yeah.
Mm-hmm. Yeah.
All right. And we're gonna get to it, and I hope just now for the proving part of this. First set of tests, there are 2 tests we just create, or is it 3 tests, which create proofs and ascertain a structure of them. So let's do that. For a given leaf index, what we need to do is we need to grab our sibling, take its hash value, take the Boolean that represents whether or not it's right on the left or right side, go to our parent, take its sibling, take the directionality, all the way to the top until we no longer have a parent, right? So again, a recursive implementation which is going to work like this. We'll have a vector containing proofs, which we're going to return. And again, we accept the leaf index, so we must convert it to an actual index. Right? Proof recursive accepts a proof, which is a mutable vector of a Boolean and a hash. We also need access to the list of all the nodes. And we need the index, which we're proving right now. So let if let some. No. Do you guys also find yourself using the let else syntax all the time? I can't stop using it. It's so good. We'll take the sibling. We'll see if we're on the right-hand side or not. That's the other way around. And proof push is left and nodes of sibling. And and just do that recursively for our parent index. And if I didn't make any mistakes, this should now work for the proof set of tests. It does indeed. If you want, we can go to these proofs again. So you'll note that for a Merkle tree of depth 2, which is exactly this situation, we set some initial value of all zeros for all the leaves. When we modify, sorry, we don't modify anything. Then we just get the proof at the first index, right? So in the proof, we expect it to be the right-hand side sibling. So the first Boolean is true. And this value will be initial value for a leaf, so all zeros, right? Then the next sibling is again true because it's on the right-hand side. And its value is a concatenation of all zero hashes, quote unquote. Same situation occurs with proof of last leaf and arbitrary proof. All good? All right. Final test, final thing we have to implement is proof verification, which just so happens to be extremely simple, as you'll just see. We'll need to return a number of nodes because that's what my test requires. And you'll notice that this verify function is not, how do you call these in Rust, like a method of a struct, right? It's a free floating function associated to this type because it doesn't actually need the access to the node, right? All we need is the proof, the leaf value we're trying to prove, and we want to return the root that we expect. So we're just going to go through the proof, grabbing each value along the way, hashing it together, and we should arrive at the root of the tree as expected. Oops. Is that correct? Is on the left-hand side. Therefore, our hash is on the left, sibling is on the right. Yeah. That should therefore verify against the expected root of the tree. There you go. This puts me at 41 minutes and a half. So almost down. I'm 4 minutes short, but I think it's fine. Do you have any questions? Yeah, sure.
Yeah. So here you made an example of a Merkle tree, which is like static, right? You cannot add another leaves to it.
Yeah.
Are there any, maybe some Merkle, any other tree which is dynamic? Because here you
yes.
have to know the maximum number of leaves. Right?
Yes, I think you always have to know the maximum number of leaves. There are tricks, but the thing you'll notice, right, is that if you want to give yourself a lot of margin, you want to pick a large depth, it grows quickly. It like grows very fast, right? So for a depth of 30, you're arriving at 40 gigabytes of data or something. But there are tricks that I'm not going to get into because I don't feel, I'm not an author of them. It's somebody developed it at work, which is to store part of the tree as a dense tree, right? So you just store the entire tree. And then each update is like a linked list. So essentially, as I mentioned in the presentation, when you update an item in the tree, all the data contained here is just the path to the top, right? So you could just store this subtree entirely in memory, but then whatever update happens to the right side of the tree, when you want to add things, is just like a linked list of these paths to the top, right? It's not going to be as efficient to update, to like calculate the root of that. And you might run, and you might like want to then have some sort of, I don't know, non-mutable data structure, but it should work. But in general, you should know the size of your tree ahead of time. Okay, any more questions? Oh, and by the way, if you want to take a look at this implementation I mentioned, where you can store a part of the tree densely allocated and then a part of the tree, linked listed, if you would, then you might want to take a look at the Semaphore RS library in the WorldCoin repository, which is the company or project I suppose I work for, and you might want to take a look at a lazy Merkle tree implementation. It's a bit verbose, but once you understand it, it's pretty clear how it works. Okay, any more questions?
Could you expand a bit more on how is Merkle tree related to cryptocurrency itself? It's like it's a bit too abstract to me.
Yeah. For example, so I'm gonna lie a little bit because, for example, in Ethereum, it's for example, in Ethereum, right? You might have these famous smart contracts, and each smart contract has a state, right? It can have values that are local to it that it can mutate, it can update as the chain progresses and moves forward. In order to like maintain and not, send all of this state every time you do a block update, we only send the data that is needed to perform the update, and then we have the Merkle tree represent the state, right? So like in Ethereum, a variable in a smart contract can be thought of as a leaf in the Merkle tree, right? So, and it's usually if you name it something like, I don't know, my variable, then you'll hash the name my variable. Sorry, not hash the name of my variable. It's based on it's like in C++, right? It's based in the order of definition. So you'll hash the number, which is index of it in the smart contract, and that will be your storage slot, right, in the Merkle tree. So you'll update that. That gives you the Merkle tree update. You only send the Merkle tree update every time a block progresses. So that's one example. Now I said I did lie a little bit because I think in practice it's not really a Merkle tree. It's something called a Patricia Merkle tree, which is another level of black magic that I don't want to get into because I don't understand it. Yeah, yet. Any more questions? Yeah.
Can you explain how the Merkle tree helps with the Git deltas?
Not really. I only skimmed over the article to have something to put in the presentation. But my understanding of it, very roughly, right, is that you'll get, like, if you have like 10 files, right, each file is a leaf in the Merkle tree. So when Git communicates with a server on the other side to verify that you have the correct version of a file, it only sends the inclusion proof. But that's, I didn't verify this, so this might not be true, but it kind of checks out, like it makes sense. And that way you only know, when you actually do a pull, you only need to download what is necessary to be up to date with the current version. All right, anything else? which puts us at 47 minutes, which is, I've overextended my welcome. However, I want to say one more thing, which is that if you think this is cool or interesting or something, we're hiring. So if you're looking for a job and want to try something new, like for example, blockchain, feel free to reach out to me. I didn't put any handles in my presentation, just after this talk, you know. And I thank you for your attention. Thank you for the time. I hope you enjoyed this. Okay. To co teraz? Przerwa? Czy zostawić?
Możesz nas zostawić.
Coś-
Okay, so let's enjoy the break. There will be some snacks, I guess, or yeah. So there will be pizza for everybody here and for everybody online. Enjoy our splash screen for a while. And then we will meet again for a second talk. Thank you very much, Jakub, for explanation on miracle trees. Very interesting indeed. Oh, the driver is calling, so sorry, but the pizza thing, right?
temat instead of editor.
Right, so you know what really gets into my nerves? My nerves. So there's one nerve in particular that I really don't like. So it's called recurrent laryngeal nerve, if I recall correctly. It's this boy. So what am I showing you? So you have larynx in here, so that's krtań in Polish, and you have some nerves which connect, larynx to your brain, as you would imagine. And one of those nerves is called this left recurrent laryngeal nerve. And instead of going, this nice clean path to here, it goes underneath your aortic arc and then back to brain. So it's like, whoop. And well, I'm sure this is not the very first instance of badly designed thing you saw in your life. So let's maybe talk about other animals, how it looks like there. So I think we've got it not that bad, actually, because, it's about, I would guess, 20 centimeters or so here. But the giraffes, oh boy. So those two white bubbles you see there, one of those is brain and the other one is, larynx. And, following the nerve template we've seen before, you would maybe expect the nerve to, span, I don't know, like in here, like through here maybe, and fuck no, it goes all the way here. And this is as much legacy code as you will see in nature as it goes. And
or grow tilt so much that it drills into its head. So it was
Oh.
kind of rounding around the it was some kind of a bore.
Yeah, I recall
There were
something.
claws which were curling and drilling into its head.
It was, yeah.
It could be worse.
I guess it could be worse. Yeah, the giraffe gets to live, so obviously the better choice. So the natural question to ask here is like, wait, why? So, what's going on here? And the question is simple. The answer is actually also pretty simple because, it all started million life years ago with fishes. And, in fish, it's more straightforward because you just have, they have the hearts closer to the brain. So this connection that goes through this aortic thingy makes more sense in their case. Then we have us, more or less like that. And then we have giraffes, so pretty wild. And with this introduction, I would like to welcome you to my talk, which is also called Wait Why, so part 2. A little bit about me. So I'm Patryk Wychowaniec. I work here at Anixa, have been for 4 years. You will find me online at my blog, where I do some Rust post series, if you're like into machine learning, genetic algorithms and stuff, so you can check it out. I try to, explain concepts from the bottom up, so no knowledge required. You will also find me on GitHub and Twitter. And with that, we can go to the actual presentation. So I'm going to show you 5 things that I've stumbled upon while writing Rust code. Those are, things that maybe not bother me in the language, but they took some time to discover, on the code reviews, or time to discover, why it worked a certain way, why it's most likely here to stay, and some rules of engagement. So I'll be doing live coding. After each of these points, we'll do a little bit of Q&A for the code that will be on the screen. So if you will have some questions to each point, I'll just, say that this is the Q&A time. And yeah, so we're starting with self-audit. And one thing. Yes, I can. And I'm also going to switch to white theme. So if somebody's on YouTube, please beware. Boom. I do not hear any screams, so went well. Right, so we're starting with self-auditing. So I'm writing some, well, first I'll write some code and then I'll ask you if you see it all right so that we have some comparison point. I might have. This one? Okay, is the font size all right? Okay, right, so we have some wrapper. Let's do some constructing work. Who can see what's wrong with this code? Nothing, it's great as it is. We'll go later and implement some print display function. So it will take one of those wrapper thingies to where we can actually display it. Sorry, I have to start Rust Analyzer to get some code hints. Okay. This one. Right. So pretty standard. We have item.item because we need to get access to the actual underlying item. And as it is right now, this code will pretty much work. Right? Simple as it is. Let's say that we want to print it twice because, you know, printing doesn't actually need to eat the item. So first of all, this code as it is will fail because obviously we are, this wrapper isn't clonable, so it gets moved into here. And one of the solutions would be to, you know, make it copy, but I don't know, let's do strings. Those cannot be copied. So naturally, if you pass a value somewhere and you don't need it to be eaten, you do a reference. So the simple solution would be something like that. But actually, it's a bit unidiomatic because it's the same case as in with option of t. So it's actually better to go with option of the reference inside. And the reason is simple, because if you have already a function that takes such an item, you can always transform it to option by just wrapping it with none, sorry, with some. So this would be something like that. This gives the option from t, while doing it the other way around. So getting ampersand option of t in this case is not possible with safe code. So like instead of this one, this is like the more useful type. But
so it's better optimized.
Might be, yeah. Yeah, it's possible that if you have option from references, it's the same size as t. Yeah. Yep.
Sorry, the pointer size. So it's word.
Pointer size there. But you know, in this case, the ampersand operator doesn't work because those are two different types, and we need a way of, you know, converting from wrapper to wrapper of ampersand t. Usually, this method is called asRef. You will find it, for instance, on option, on result, I think also. And it's pretty simple to implement. So we do asRef. It returns wrapper of ampersand t. And the item is borrowed. And this is the place where the code breaks, as it is right now. And the error message is kind of, I think, semi-helpful, because it says, maybe I'll show it like that so that it doesn't wrap. It says mismatch types. It says that it expected wrapper of ampersand t, and we return it wrapper of t. And if we take a look at the code, this can be a bit baffling because we do build a new wrapper that we pass, you know, ampersand into. And does somebody want to guess what's going on here? Okay, let me show the whole code. Yeah.
Type help is the type of your entire input.
Yep.
Which is help.
Yep. So this is, you know, pretty simple mistake. It can be difficult to spot because it doesn't actually mention, you know, the fix in display in the error message. But the thing is that the self always refers to what's inside the at the beginning of the input block. So it's as if the code here did something like that, which obviously doesn't make sense. It should be ampersand or just, you know, elided whatsoever. So simple, but it can take a few minutes. All right. Now something a bit more difficult. Let's say that we have database connector. If you know databases, you know that they have concept of transaction. So if you run a query in a database, transaction allows you to confirm that you want to save the changes or, you know, cancel them. And in our design, let's say that it takes database as an, you know, owned value. Customarily, the method that actually saves the changes is called commit, because it ends the transaction. We can just, you know, take self. And let's say that the actual implementation is in a separate function that, you know, takes database. Because I don't know, we can have database commit as well, and, you know, this way you can reuse the stuff. There is some reason for that. As it is right now, the code will work. So if we do transaction db database commit, it will compile, though obviously it doesn't actually do anything. But there is a place, there's a way to make this code break by not changing anything inside this block. And I think this is one of the few cases where actually adding a trait implementation breaks your semper guarantee. So if this was already released as version 1, if now you do input drop, this can be actually a breaking change, and you would need to release version 2. And the reason is simple, although the error message in this case is also not so clean. It says that we cannot move out of transaction because database does not implement copy. And, you know, in this actual example, we could just derive copy, but if we imagine that there is some actually, I don't know, some socket in here, some actual code where we cannot do copy, then this breaks. And the problem with this is that the destructor is always called after the item gets out of scope. So it's as if the compiler added here self-drop, and the compiler doesn't care about that we don't access the database in here. From what it knows, we could do something like, you know, even just print it. And if we did, this code will be invalid, because if we move the database from ourselves into commit, and then the database gets dropped in here, we just don't have it in here anymore.
Why doesn't the structure run at the moment we move the first field out of the struct?
Mm-hmm.
Actually, when you reference the DB member, at this point our structure should get sort of structurally decomposed.
Mm-hmm. My rough guess is that you can have what's called partial borrow, partial move. So for the sake of argument, let's just have two databases. And this is obviously valid because each of the, I mean, you know, if not for the drop block, on its own, this is valid. We can move the first and then the other one. But for instance, if we had a field in here that was, I don't know, int, where is the place that we should call drop? Is it in here? So like in here or in here? Because only this is the place where you don't have, the rest of the types are, you know, not copyable.
Right. Well, the idea is that when you drop something, the idea of dropping the source of this is to release resources. So basically to drop everything, the structure out. So if the job will be called anywhere before it was passed to some function, then every field of the structure will be dead. So you cannot drop it at all, right?
Would matching here help?
Yeah, so destructuring, no, because destructuring is the same case. So it works when you don't have destructor. Well, in this case, this should be just DB, obviously. as soon as we add a destructor, the type is not destructible.
Right.
Yeah, I forgot the word. Yeah, destructible anymore. Well, for the same reason, so this would be the same. It suggests to add ref, which partially solves the issue because then you have ampersand database in here, but it doesn't help you in actually invoking do commit because you need owned DB for that. And actually, usually when you have like database connector in Rust, this is not an abstraction. This is actually a pretty useful thing to have. And for a reason I'll show right now. So first of all, how do we solve this issue? Because assuming we need have access to the database in the structure, we might have. One of the solutions here is to make it optional. And then when you create the transaction, you always assign it to some, so that it starts, as visible. And then when you need to have the owned version of your inner type, you use a function called take. It's a function option. When option is some, takes return you the inner value. When the option is none, it returns you, well, none. So we'll take unwrap, and this solves the issue. I only make it mutable. And this also solves the issue with the destructor, because then inside the destructor, you just don't have the DB anymore. So if we do something like that, it will say false. And the way it's usually used is that if we imagine that we actually have some code that is able to run transactions, like queries, so like something like that maybe. Okay, then let's say we have something similar on the transaction. And then first of all, we cannot just do self DB query because it's option. So in this case, first we call asref to get option of database, then unwrap, then we have the query. And the way this pattern is used then is that inside the drop, we can check if the database is present. If so, then we can force the transaction to get rolled back. So in here, if we imagine that the do commit, just queries to the database, I don't know, save changes. Then inside here, we can query database with undo changes. And in the other hand, commit must have been already called because otherwise we would have the database. And this is useful because then if we have a transaction, we can do query something. And in this case, we will see something and then save changes. But if we forget about commit, we will automatically get something and undo changes because the destructor is always called, unless panic in a destructor, but let's say it's always called. And if we have the database in this case, because commit was not called in this flow, then we can do something extra. Otherwise, we've lost the database. So this is pattern you will see frequently in various database connectors. I know Redis clients, possibly not because they don't have transactions, but like with relational databases, it's pretty common. And then one thing, so this unwrapping might seem funky, like, where does it actually panic in this case? Because clearly in the happy scenario, it all just works. So why do we need option in the first place? And the issue is that you could technically call query from in here. And then if you call commit, then this code will panic. So like that. Because you try to query, but you don't have the database anymore because you've already dropped it while doing commit. So this unwrap is actually something like query called inside drop. So this is the edge case it, this is the edge case it got us from. All right, so any questions for this part? Yeah.
Beginning of the part,
Uh-huh.
I think you claim that there's the only situation when implementation of a trait.
One of those, one of few. Oh, yeah. Because I know that you have also like send, sync, auto traits you can implement.
Kind of implementation of any trait.
No, actually, the way it's designed is that specifically with regards to orphan rules is that usually, if not for drop and auto trait, you can always add a new trait, a new implementation of your trait to your type, and it's not a breaking change.
But I'm wondering what the situation when user auto type
Mm-hmm.
is sourcing, like using
Mm-hmm.
your two traits,
Mm-hmm.
one your trait you are not implementing,
Mm-hmm.
and another trait which was implementing before on your type with the same single function. And now this function is no longer callable directly and you need to use the unified function.
In this case, yeah, I think it's a gray area. So it's the same case as if with star imports. So in principle, adding a new type is not a breaking change either. But if you have star import, then it could be, because you could have create A, source everything from there. And if we say that there's a type foo, currently only in crate A, so then if crate B also has a type called foo, then it's kind of sort of breaking change because you have ambiguity now.
Yeah, that situation, and here you don't need to just need to the both trait before completely names. No, because you could use the trait for chemicals,
you could
and it will just implement the side.
Mm-hmm.
I know it's a case, and I know it's a situation. I'm just careful about.
Yeah, I think the rules regarding, the precise rules regarding breaking semantic versioning are still like being developed. So.
Remember, I faced this issue. That's my thing.
Mm-hmm. All right, anything more before I, drop this code and drop this code? Yeah.
I just have a question slightly related.
Uh-huh.
Is bounding minimum supported draft version a breaking change or not?
That versions were dropped essentially by advisory. It's not
Yeah?
advice anymore.
Oh, wasn't that way?
Whoa. I mean, it's not. There was some change, maybe not drop, but there was some discussion about that.
Mm-hmm. That's nice.
Because of issues with creators. But I don't have some time. So.
All right. Well, then we have no derive, no cry. So this also comes up quite often when you work with generic types. So let's say that we are not very innovative, so we just want to write a list. Well, probably should have called just vec2 because this won't be linked list, just wrapper for vec, so items vec_t. Let's add some function such as push. Yeah. And let's add a derived default so that we can actually, create instances of this list. So list default. Yeah. Like that, and obviously also debug in this case. And as it is, this code will work. It's slightly broken in a way that's difficult to see on the first side. I mean, broken depending on how you define it. I would define it as broken. And the issue comes up when inside this list, instead of using something like &str, we'll use something that doesn't have default constructor. So let's say we have some myString. Like that. And now the code will say, the compiler will say that myString doesn't implement debug. How true? But not this one. And that myString default is not, it's not, how is it precisely? Just implemented, right? Because the message is a bit cut, but the trait bound myString default is not implemented. And intuitively, this doesn't make sense because if we replace this with vector, then this code works. And rightfully so, because we don't actually need empty string well, we don't have empty string anywhere in here. So why would it be required to use it with our list? And this is a problem known as implied bounds and perfect derive. There's a great article from Nico Matsakis on this subject. If you Google these 5 words, you will find it. But to briefly say it, most derive macros, when you use them, add the same bound to the t type you have in there, whatever types you have in there. So what this code expands to, if we did it by hand, is impl t default for list t, where t is also default. And then it's like that. And this bound is overzealous because we don't actually need for t to be default to implement this type, because this is as easy as this. And this will actually solve our problem. And the reason why the compiler does it this way is for also kinda related to Semver, kinda because of compiler troubles in the past with self-referential types, because in principle the bound we need here is vect implements default, and then vector implements default for all of the types, so this would be also an all right thing to do. And why the compiler does the overzealous version of just assigning t is that in the past the compiler had troubles with referential types. So if we say we have something like that of parent list, in our perfect version, this would have to generate bounds such as this is default and option from self is also default, which takes a while to settle on, but let's say. And because this self here is self-referential bound, the compiler in the past, a few years ago, had troubles with proving that this impulse default, because, well, POV, you are compiler, you are trying to check if this is valid implementation, so easy one. And then you have to check if option of self is default. Oh, great, so for that I have to check if this holds. Oh, okay, this holds. Oh, okay, we're back to square one. Now the compiler understands this. If I just added box here, and then this technically should be box self, and this will work. But the old logic state for one important reason also, which is that usually when you add a new private item into your type, this is not a breaking change. So we could add something like, I don't know, item t, whatever, and with this automatic generated bound, which is too much, but it would actually wouldn't be a breaking change, because this bound was here before and it is right now when we added it. But with the initial mechanism, so with the proposed perfect derive, this would be the first impl, then we add this bound, this creates a second impl, even though the only thing we've done was modify some private field somewhere deep in your type graph. And this is already a problem with auto traits such as send or sync, because this is exactly what they do. You can add some random type somewhere, and suddenly, even though you don't spot it on the first sight, your type is not send or sync anymore. And this is frequent source of frustration for when you bump a version of your crate. Well, not your crate, somebody's crate in your program, and then your asynchronous code stops working because someone somewhere added some magic type that propagated up into your struct somewhere. And this is why the current logic of using just the generic bounds you passed instead of the actual types is pretty much here to stay. Those cases can be a bit difficult to spot because, well, in this case, I've showed you, for instance, with list and vector. So what you should do instead of doing derive debug is just implement the default by hand. But some cases are a bit more tricky. For instance, if we had another kind of wrapper, and if we do derive clone, then we're back to square one because we don't actually need for the t to be clonable to clone arc of t. So this would actually also need to be changed from derive to manual implementation that calls arc clone. Or I think there's a crate called derivative that you can use to automatically generate it. I think probably something like that, if you don't really writing by hand. But it's important to at least be aware that sometimes doing the derive way is not actually the best way, even though the the generated code kinda looks like boilerplate that the compiler could have done in the first place. Right? Any questions for this part?
You meant the generated code or the generated code?
Oh snap, I lost context on that sentence, so I'm not sure what I meant. Could you say a bit more?
No, just my brain.
Right? So also I'm curious about one thing in this case before we go further, which is if Clippy catches this case. Okay, let's comment this out. Oh no, so it doesn't catch this. So you have to just be aware, or maybe write a lint for that. If you have some time, this would be useful. And the actually related part is trait called deref. So you might probably use deref even if you don't actually know that it was called there. And to understand it, let's focus on this part. Let's say string from hello. So somewhat predictably, this works. And when you box this, this also works, but this begs a question, why does it work? Since there is a function on string for length, but there is no function on box for getting the length. So if you do something like that, and this actually fails because you cannot have, well, yeah, this doesn't make sense. So what is the magic here that allows you to call length through the box, or other types such as arc or RC, or actually in this case string itself, yeah. And this trait is called deref. We can go back to the list thingy, and there's a trait called, as I said, deref. And deref is a trait which compiler invokes on a few occasions, mostly when you do the dot operator. And what the deref operator does is that it allows you to specify that your type is like a wrapper for something. So in this case, we might imagine that the list is just a wrapper for a vector, and we can just return it. And what the code will do now, if we go back to some useful field list, is that now on our items stuff, instead of having just the pass function as we would have otherwise, we can call everything that the vector also has. So we can, for instance, call len, and this will work if I just make it mutable in here. That's two. And this is mostly useful for things like boxes. Although I do also have a few uses for types that wrap something and then provide extra functions, kind of like trait extension style. And there's also like cousin to this function, because the ref also only grants you read access. So you couldn't have done something like, probably easiest to just remove the pass function in this case, because vector also provides a pass function, but we cannot call it yet because we have not implemented the ref mode. And it just refers to the item. And if you, for instance, use Baby, which is the Rust crate for making games, then you might know that Baby also uses this pattern to track changes when something has changed. Because if you have just the ref, then we know that the item, the value we return couldn't have been changed. But if we use the ref mode, we can toggle something like, I don't know, dirty to true. And then we can know that some collection was probably modified if the ref mode was called. And the reason why I'm mentioning this trait is that actually I had a case in my job when I had something like that, I think. It was, I think, also a wrapper for some type. And usually, the target type in here doesn't have to be so specific. It doesn't have to be sized even, because we always return it through a reference. Then it could be a nice idea to return like more useful type in here. So if in the future, instead we imagine that instead of using vector, our implementation switches to, I don't know, some box of slice, whatever, and in some magic way we implement push, then if we direct to vector, then this wouldn't work because it's obviously not a vector. But with slice it would, so it's a good idea to keep the type in here, more abstract. And I refactored code that was using it, and I broke it because there was one place in code that was calling, I think, capacity. And I think it then either stopped working downstream. So I had, my crate, I committed the changes, and then, some crate downstream broke. And so this is like more kind of beware. So if you're writing from scratch, then it's a good idea. But if you refactor in, then probably, switching types to the more general ones doesn't always help. Right, any questions for the ref part? Nice. This brings us to the last case, smells like lifetime extension. This is quick of the language, I would say. So I will go back to text mode so that it doesn't actually underline what the issue is. And I'll write 2 lines of code where one of them will be legal and the other one will be not. And they both look like they shouldn't be legal. So string new. Right, they do kind of different thing, but let's maybe call one of them so that makes kind of sense. And you can do a quick question round. So who says that this code will not compile whatsoever? Both are broken. Okay. Who says that the first one, just the first one is broken?
First one is broken.
Just the first one is broken. Okay, and who thinks just the second one is broken? Okay. Yep, so just the second one is broken. And the reason is kind of, should be this one, yeah. And the reason is that there is a mechanism in Rust called lifetime extension. It kicks in cases where we have ampersand of expression of, something. And what the compiler does in this case is something akin to string new, and then including where the value gets dropped. So this is just like a shortcut for doing this. And the other one, in this case, the compiler allocates string new, and then you try to reference something when it's dropped. So this is more like, format it. So this is more as if you've written something like that, which is obviously wrong because you allocate the string dice in here, so we cannot return something from the string in here. But ampersand something is like edge case. It's simply defined to be working this way, and it comes useful at few occasions. You might have even used it without being aware, because one of the cases where this will get kicked in is something like this. So this uses this mechanism of lifetime extension twice. Contains at this function. So first of all, this contains is not defined on a vector, it's defined on a slice. So what the compiler needs to do is something like that, numbers. So let's make that tmp1. Then has to, maybe if I annotate the types in here, then has to call the deref operator to do something like that. Well, tmp1, which transforms it to slice. Then we have the third temporary, which is just the free. And then what actually the code in here does is just tmp2 contains tmp3 or, ampersand. And so if you were wondering, like, what's the random use case for ampersanding stuff? So the ampersand is just like a side effect. The major use case for that is so that you can call stuff without actually having to worry where this data gets released in a few useful cases, such as this one. Because this would be this is way more verbose that just, numbers contains whatever you want.
I think it's quite common in the Rust book, in some test implementations. I remember seeing it coming from C and C++ and being super confused. What are you doing? Where's the legal?
Yeah, there are some cases. Although obviously if you're trying to, in one place, do something like numbers, get to unwrap, then this will work in this case. But if you try to assign it, and this will not, because and now I'm baffled. Maybe I have to use X and do something like that to bring the scope, where I want it. Right, and I have to actually return this value. So something like that. Oh no, now it's temporary that gets dropped. Right, yeah. Which begs the question, if now I wrap it like here. Okay, yeah, right, so any questions for that, or any of the previous ones, since this is the last case I have?
The general public consider the foundation or something, or any inconvenience.
I think it's a neat convenience. To be fair, I had it written down for like a few months now, but I don't recall where it popped up in code. I read it because there's a dedicated chapter either in the Rustonomicon, so like the secrets of Rust book, or I think even in the main book. And there's a dedicated chapter on lifetime extension and where it triggers. Also regarding the scoping, so where if you do this ampersand thingy, what is the actual scope of the variable you're creating this way. I think it can be surprising. So for a brief moment, I thought that this could work, for instance. Now I know that it won't. But overall, I think it seems helpful.
I think it depends only on the server first. That's why it doesn't work, and that's why it's basically reasonable. It doesn't ruin anything because it's running only on top level where we don't need the ownership anymore. You can say, okay, it's now there's no ownership.
All right. In this case, thank you so much for listening. I'll try to have some more fun cases for now, because I think this was the second part, so I've shown all 10 cases from Rust I had, but hopefully some code reviews and PRs will bring some more stuff. Thank you. Great.
So thank you all for coming and from joining the stream. See you on the next event, which we don't know the date yet, but we should announce it soonish. But anyway, we have a LinkedIn profile from some time that maybe you would like to, I don't know, like or whatever. We have a Rust Wrocław website, and most importantly, we have Rust Wrocław Slack. You can find it all on the website. That was Ah, do you have it?
Yeah, I can. Yeah.
Okay, yeah, this is the site. So it's Rust-Wrocław PL. You can find a link to Slack, and I guess we should add LinkedIn here. And yeah, anyway, thank you all.
And we're going to somewhere to Nasib probably now.
Oh yeah.
We'll see. I mean, but that's not for online. We'll set
Yeah.
it up.
Yeah. We won't bring our camera to Nasib for an after party. So if you would like to hang out with us, I guess you will need to come in person for the next meeting. So thank you all, and bye bye online guests, and yeah, let's enjoy some after party.